and we end this chapter with the first test that we looked at, namely testing for normalcy. Now this test is crucial because pretty much all of the other tests that we looked at require the underlying populations of our samples to be normally distributed in order for these tests to be valid. And that is why you will almost always start your data analysis with the Shapiro-Wilk test, which indeed tests for normalcy. But what now if this test fails? What if you cannot confidently conclude that your sample is drawn from an underlying normal distribution? Well, this brings us to non-parametric tests. These are alternative tests to the tests that we looked at, the parametric tests, which require normalcy. Now, don't be afraid, because the reasoning of these non-parametric tests remains exactly the same. The only thing that changes is this distribution of sample statistics against which we compare our own sample statistic. Now, what we lose, however, is that in general, non-parametric tests are less accurate, meaning that the conclusions that you draw from these tests will be less confident, except of course if your p-value is really, really low or really, really high. Now it turns out that each of the tests that we looked at has a non-parametric alternative. So this test you should use in the case that the Shapiro-Wilk test fails. So let's go through them now one by one. Now there are some difficult names, so my apologies for any mispronunciations. If you want to test for equal variances, then in the parametric case, meaning the Shapiro-Wilk test succeeded, you had the Levene's test, and the alternative non-parametric test is the Brown-Forsythe test. If you want to test for equal means between two populations that are independent, then you have the independent student t-test, and the alternative is the Mann-Whitneyu test. For equal means with paired populations, we have the paired student t-test, and the alternative is the Willcoxon test. And then if you want to test the means of multiple populations, you had the ANOVA test for the parametric case, the analysis of variances, and the alternative will be the Kruskal-Wallis test. Now, fortunately, in the same way that these parametric tests were all easily computed in Python with just one line of code, the alternative tests will be equally easy to compute, also with just one line of code. So let's now see how this is done in practice. As was the case in the previous lesson, we will here generate 3 populations, and again 3 samples, one for each population. However, the 3 populations in this lesson will be 3 non-normal populations. So in each of these cases, the Shapiro-Wilk test will fail in the majority of the times, of course depending on your sample size and your statistical significance. But the important thing is that we know here that the underlying populations are not normal. So let's dive into the code and see how we can compute these alternative tests. And as always, we start by defining our populations. Now, as I said before, in this case, we will explicitly make sure that none of our populations are normally distributed. We have a Rayleigh distribution for population 1, an exponential distribution for population 2, and a uniform distribution for population 3. And we generate our samples, one for each population, with a sample size of 50. And then we already make the figures for our histograms. Now, this by now is incredibly familiar. We plot the histogram of population 1, histogram population 2, and the one of population 3 on the first row of figures, and then correspondingly the histogram of sample 1, sample 2, and sample 3 on the row of figures below that. And we do this to visually show that our samples in these cases are definitely not coming from normal distributions. So if we then scroll down and we get to the numeric part. Now, because we want to showcase these alternative non-parametric tests, we need to simulate the corresponding scenarios. Therefore, the scenario of comparing the variances and comparing the means of the underlying populations. Therefore, we of course need to first compute the population statistics and the sample statistics. So we first compute the population means and the population variances. And the same we do for the sample means and the sample variances. And at this point, of course, the same challenge as before faces us. Can we, judging by our sample statistics, deduce any of the same differences in the underlying population statistics. And this time, of course, where the populations are explicitly not normally distributed. So let's get to our tests. And in the first case, we want to test for equal variances of our underlying populations, based, of course, on our sample variances. Now, previously, this would be the Levene's test, but now the alternative non-parametric test is the Brown-Forsythe test. And this can be done quite easily. We define BF test as being stats.levene, indeed the same function as computing the Levene test. But the difference here is that we give it this parameter center to be median. And this will tell this function that we're actually looking for the Brown-Forsythe test and not the normal Levene test. We of course give it sample 1 and sample 2, and then we plot the result inside of an F string, where we just round our p-value to 3 decimals. The next step is to compare means with each other. And this splits out into two depending on the context of our sample dataset, this independent or paired scenario. In the independent scenario, we look at the alternative for the independent t-test, which was this Mann-Whitneyu test. Now this can be very easily done by defining our test being stats.Mann-Whitneyu, and then give it sample 1, sample 2, and we abstract the p-value by looking at the element with index 1. And we again print this result in our F string. Then for the paired scenario, we look at the alternative for the paired t-test, which will be the Willcoxon test. We define a variable, we put it equal to stats.Willcoxon in this case, and we give it sample 1 and sample 3. And the p-value is abstracted by looking at the element at the index 1. And we again print our result. And the last scenario that we will look at is when we want to test for equal means between more than just two populations. Now, in the parametric case, when normalcy is fulfilled, this was done by the ANOVA test, or the analysis of variances. But in this alternative non-parametric case, this test will be the Kruskal-Wallis age test. Now, as before, this is done quite easily by just putting stats.Kruskal and then giving it our samples to test from. And the p-value is obtained by looking at the element at position 1. Now again, we can print this result in an F string where we show this p-value rounded up to 3 decimals. Now if we run this cell and we scroll down, then we see our results. Well, first of all, the figures that we plotted, which clearly show that the underlying populations are not normally distributed, but more interesting is the collection of print statements that we made, containing all of the p-values and the underlying statistics. So what can we see? First of all, we have our population statistics, and they will serve as a ground truth against which we can compare the conclusions that we get from our p-values. We can see, for instance, that the mean of population 1 and population 3 are somewhat equal to each other, but also that the variance of population 1 and the variance of population 3 are roughly equal to each other, and that population 2 is somewhat the odd one out. So let's first look at the equality of variances, the variance test, or the alternative for the Levene's test. The Brown-Forsythe test for equal variances gave us a p-value between sample 1 and 2 of 0.001. And such a low p-value allows us to conclude that, judging by the difference in sample variances between sample 1 and sample 2, the variances of the underlying populations are also indeed different. And that is of course what we see in our reference populations. Now for the sample means, we had several tests. First of all, the sample means themselves. For sample 1 we had 1.275, for sample 2 2.035, and for sample 3 1.267. Now the first test was the alternative for the independent t-test. So if you have data sets that are independent, the alternative test is the Mann-Whitneyu test. And we got a p-value for sample 1 and 3, so comparing this number and this number, of 0.385. Now this is a large p-value which allows us to accept the null hypothesis. And the null hypothesis is that the means of the underlying populations of these samples are indeed equal to each other. And that is indeed what we can see in our reference populations. These means are roughly equal to each other. Now, if our underlying samples were coming from paired data sets, then we had to do the Willcoxon test. In this case, we got a p-value, again, between sample 1 and 3 of 0.927. Now, this is even larger, and this also allows us to accept the same null hypothesis. And the last test that we did was the Kruskal-Wallis test. This was the alternative for the ANOVA test, testing whether the means of the underlying populations of multiple sample sets are also equal to each other. And in this case, we got a p-value of 0.035, so lower than 0.05, our statistical significance. Now, this allows us to reject the null hypothesis that all of the underlying population means are equal to each other. However, as was the case for the ANOVA test, it does not show us which population mean is different from the others. And indeed, we see that this population 2 is the odd one out. So also this test reflects the right underlying situation. So let's now go back to the slides and conclude this chapter on statistical testing. The important thing to take away from this chapter is that you really understand the logic and the reasoning behind statistical testing, and that you know how the underlying mechanism works. Now, we went over this in detail both in the slides, but also by going through the code and implementing this reasoning. And therefore, it is not important or even useful to know all of these statistical tests by heart or even remember their names. If you need a specific test, you can always look it up. What is important, however, is that you realize that each statistical test comes with its own requirements, which then in turn can also be checked with statistical testing. Now, in particular in this chapter, please use these Jupyter notebooks to play around and change these parameters and see how they influence the results, and thereby simulating different scenarios. This will build your intuition in this very important subject. Now, in the next chapter, we won't be learning any new concepts, but we will see some very neat examples where statistical testing allows us to make some very cool conclusions. So I will see you in the next chapter.